Chapter 2. Mechanical Properties of Fluids. Exercises pages 54 to 55. Exercises Q1.1, page 54. Multiple choice question. A hydraulic lift is designed to lift heavy objects of maximum mass 2,000 kilograms. The area of cross-section of piston carrying the load is 2.25 times 10 to 2 m2. What is the maximum pressure the smaller piston would have to bear? 1. 0.8711 times 106 Nm2. 2. 0.5862 times 107 Nm2. 3. 0.4869 times 105 Nm2. 4. 0.3271 times 104 Nm2. Solution. 0.8711 times 106 Nm2. Exercises Q1.2, page 54. Multiple choice question. Two capillary tubes of radii 0.3 cm and 0.6 cm are dipped in the same liquid. The ratio of heights through which the liquid will rise in the tubes is 1. 1. 2 2. 2. 1 3. 1. 4 4. 4. 1. Solution. Exercises Q1.3, page 54. Multiple choice question. The energy stored in a soap bubble of diameter 6 cm and T equals 0.04 N per meter is nearly 1. 0.9 times 10 to 3 J2. 0.4 times 10 to 3 J3. 0.7 times 10 to 3 J4. 0.5 times 10 to 3 J. Solution. 0.9 times 10 to 3 J. Exercises Q1.4, page 54. Multiple choice question. Two hailstones with radii in the ratio of 1:4 fall from a great height through the atmosphere. Then the ratio of their terminal velocities is 1. 1. 2 2. 1 12 3. 1 16 4. 1. 8. Solution. 116. Exercises Q1.5, page 54. Multiple choice question. Bernoulli theorem is based on the conservation of 1. Linear momentum 2. Mass 3. Energy 4. Angular momentum. Solution. Energy. Explanation. The principle behind the Bernoulli theorem is the law of conservation of energy. It states that energy can be neither created nor destroyed, it merely changes from one form to another. Exercises Q2.1, page 54. Why is the surface tension of paints and lubricating oils kept low? Solution. For better wettability, surface coverage, the surface tension and angle of contact of paints and lubricating oils must be low. Exercises Q2.2, page 54. How much amount of work is done in forming a soap bubble of radius r? Solution. We know that a bubble has two surfaces in contact with air, so the total surface area of the bubble will be equals 2 times 4 pi r2 equals 8 pi r2. Now, work done equals surface tension times increase in surface area equals T times 8 pi r2 minus O equals 8 pi r2t. Exercises Q2.3, page 54. What is the basis of Bernoulli's principle? Solution. Conservation of energy. Exercises Q2.4, page 54. Why is a low-density liquid used as a manometric liquid in a physics laboratory? Solution. An open tube manometer measures the gauge pressure, P, PO equals HPG, where P is the pressure being measured, PO is the atmospheric pressure, H is the difference in height between the manometric liquid of density P and the two arms. For a given pressure P, the product HP is constant. That is, P should be small for H to be large. Therefore, for noticeably large H, a laboratory manometer uses a low-density liquid. Exercises Q2.5, page 54. What is an incompressible fluid? Solution. An incompressible fluid is one which does not undergo a change in volume for a large range of pressures. Thus, its density has a constant value throughout the fluid. In most cases, all liquids are incompressible. Exercises Q3 page 54. Why two or more mercury drops form a single drop when brought in contact with each other? Solution. A spherical shape has the minimum surface area to volume ratio of all geometric forms. When two drops of a liquid are brought in contact, the cohesive forces between their molecules coalesce the drops into a single larger drop. This is because, the volume of the liquid remaining the same, the surface area of the resulting single drop is less than the combined surface area of the smaller drops. The resulting decrease in surface energy is released into the environment as heat. Proof. Let n droplets each of radius r coalesce to form a single drop of radius r as the volume of the liquid remains constant. Since the bracketed term is negative, there is a decrease in surface area and a decrease in surface energy. Exercises Q4 page 54. Why does velocity increase when water flowing in broader pipe enters a narrow pipe? Solution. When a tube narrows, the same volume occupies a greater length, as schematically shown in figure. A1 is the cross-section of the broader pipe and that of the narrower pipe is A2. By the equation of continuity, V2 equals A1, A2, V1. P of fluid increases as it enters a narrower pipe, not drawn to scale. Since A1, A2 greater than version 2 greater than version 1. For the same volume to pass points 1 and 2 in a given time, the speed must be greater at point 2. The process is exactly reversible. If the fluid flows in the opposite direction, its speed decreases when the tube widens. Exercises Q5 page 54. Why does the speed of a liquid increase and its pressure decrease when a liquid passes through a constriction in a horizontal pipe? Solution. Consider a horizontal constricted tube. Let A1 and A2 be the cross-sectional areas at points 1 and 2, respectively. Let version 1 and V2 be the corresponding flow speeds. Rho is the density of the fluid in the pipeline. By the equation of continuity. Therefore, the speed of the liquid increases as it passes through the constriction. Since the meter is assumed to be horizontal, from Bernoulli's equation we get. Again, since A1 greater than A2, the bracketed term is positive so that P1 greater than P2. Thus, as the fluid passes through the constriction or throat, the higher speed results in lower pressure at the throat. Exercises Q6 page 54. Derive an expression for excess pressure inside a drop of liquid. Solution. Consider a liquid drop of radius r and surface tension T. Due to surface tension, the molecules on the surface film experience the net force in the inward direction normal to the surface. Therefore there is more pressure inside than outside. Let P1 be the pressure inside the liquid drop and P0 be the pressure outside the drop. Therefore, excessive pressure inside the liquid drop is P equals P1 P0. Due to excess pressure inside the liquid drop, the free surface of the drop will experience the net force in outward direction due to which the drop will expand. Let the free surface displace by Dr. under isothermal conditions. Therefore, excessive pressure does the work in displacing the surface, and that work will be stored in the form of potential energy. The work done by an excessive pressure in displacing the surface is dW equals force x displacement equals excessive pressure x surface area x displacement of the surface equals P times 4 pi r2 times drive 1. Increase in the potential energy is dU equals surface tension x increases in area of the free surface equals T 4 pi r plus Dr 2 to 4 pi r2 equals T 4 pi 2 r dr. Dot opening parenthesis 2. From 1 and 2. P times 4 pi r2 times Dr equals T 4 pi 2 r dr. Exercises Q7 page 54. Obtain an expression for conservation of mass starting from the equation of continuity. Solution. Consider a fluid in steady or streamline flow, that is, its density is constant. The velocity of the fluid within a flow tube, while everywhere parallel to the tube, may change its magnitude. Suppose the velocity is at point P and At point Q, if A1 and A2 are the cross-sectional areas of the tube at these 2 points, the volume flux across A1. Since no fluid can enter or leave through the boundary of the tube, the conservation of mass requires the mass fluxes to be equal, i.e. Exercises Q8, page 54 explain the capillary action. Solution. When a capillary tube is partially immersed in a wetting liquid, there is a capillary rise and the liquid meniscus inside the tube is concave, as shown in figure A. Consider 4 points A, B, C, D, of which point A is just above the concave meniscus inside the capillary, and point B is just below it. Points C and D are just above and below the free liquid surface outside. Let PA, PB, PC, and PD be the pressures at points A, B, C, and D respectively. Now, PA equals PC equals atmospheric pressure. The pressure is the same on both sides of the free surface of a liquid, so that explanation of A capillary rise, B capillary depression. PC equals PD. Therefore PA equals PD. The pressure on the concave side of a meniscus is always greater than that on the convex side, so that PA greater than PB. Therefore PD greater than PB. Because PA equals PD. The excess pressure outside presses the liquid up the capillary until the pressures at B and D, at the same horizontal level equalize, i.e., PB becomes equal to PD. Thus, there is a capillary rise. For a non-wetting liquid, there is capillary depression and the liquid meniscus in the capillary tube is convex, as shown in figure B. Consider again 4 points A, B, C, and D when the meniscus in the capillary tube is at the same level as the free surface of the liquid. Points A and B are just above and below the convex meniscus. Points C and D are just above and below the free liquid surface outside. The pressure at BPB is greater than that at APA. The pressure at A is the atmospheric pressure H and at D, PD asymptotically equal H equals PA. Hence, the hydrostatic pressure at the same levels at B and D are not equal, PB greater than PD. Hence, the liquid flows from B to D, and the level of the liquid in the capillary falls. This continues till the pressure at B is the same as that D, that is till the pressures at the same level are equal. Exercises Q9, page 54 derive an expression for capillary rise for a liquid having a concave meniscus. Solution. Consider a capillary tube of radius r partially immersed into a wetting liquid of density ρ. Let the capillary rise be h and theta be the angle of contact at the edge of contact of the concave meniscus and glass figure. If r is the radius of curvature of the meniscus, then from the figure, r equals r cos theta. Analyzing capillary action using Laplace's law for a spherical membrane. Surface tension T is the tangential force per unit length acting along the contact line. It is directed into the liquid making an angle theta with the capillary wall. We ignore the small volume of the liquid in the meniscus. The gauge pressure within the liquid at a depth h, i.e., at the level of the free liquid surface open to the atmosphere, is P0 equals ρ gh. Opening parenthesis. 1. By Laplace's law for a spherical membrane, this gauge pressure is. Equations 3 and 4 are also valid for capillary depression H of a non-wetting liquid. In this case, the meniscus is convex and theta is obtuse. Then, cos theta is negative but so is H, indicating a fall or depression of the liquid in the capillary. T is positive in both cases. Note, the capillary rise H is called Jurin height, after James Jurin, who studied the effect in 1718. For capillary rise, EQ3 is also called the ascent formula. Exercises Q10, page 55 find the pressure 200 meters below the surface of the ocean if pressure on the free surface of liquid is 1 atmosphere. Density of seawater equals 1060 kg per cubic meter. Solution. Data. H equals 200 meters, P equals 1060 kg per cubic meter. P0 equals 1.013 times 105 pascals, G equals 9.8 meters per square second. Absolute pressure. P equals P0 plus HPG equals 1.013 x 103 plus 200 x 1060 x 9.8 equals 1.013 times 105 plus 20.776 times 105 equals 21.789 times 105 equals 2.1789 megapascals. Exercises Q11 page 55. In a hydraulic lift, the input piston had surface area 30 square centimeters and the output piston has surface area of 1,500 square centimeters. If a force of 25 N is applied to the input piston, calculate weight on output piston. Solution. Exercises Q12 page 55. Calculate the viscous force acting on a raindrop of diameter 1 mm, falling with a uniform velocity of 2 meters per second through air. The coefficient of viscosity of air is 1.8 times 10 to 5 nsm2. Solution. Exercises Q13 page 55. A horizontal force of 1 N is required to move a metal plate of area 10 to 2 m2 with a velocity of 2 times 10 to 2 meter per second, when it rests on a layer of oil 1.5 times 10 to 3 m thick. Find the coefficient of viscosity of oil. Solution. Exercises Q14 page 55. With what terminal velocity will an air bubble 0.4 mm in diameter rise in a liquid of viscosity 0.1 Ns per square meter and specific gravity 0.9? Density of air is 1.29 kilograms per cubic meter. Solution. Data. D equals 0.4 millimeters, eta equals 0.1 pascals. S, rho L equals 0.9 times 103 kilograms per cubic meter equals 900 kilograms per cubic meter. Rho air equals 1.29 kilograms per cubic meter, G equals 9.8 meters per square second. Since the density of air is less than that of oil, the air bubble will rise up through the liquid. Hence, the viscous force is downward. At terminal velocity, this downward viscous force is equal in magnitude to the net upward force. Viscous force equals buoyant force, the gravitational force. Exercises Q15 page 55. The speed of water is 2 meters per second through a pipe of internal diameter 10 centimeters. What should be the internal diameter of the nozzle of the pipe if the speed of the water at nozzle is 4 meters per second? Solution. Exercises Q16 page 55. With what velocity does water flow out of an orifice in a tank with gauge pressure 4 times 105 nm2 before the flow starts? Density of water equals 1000 kg per cubic meter. Solution. Data. P0 equals 4 times 105 pascals, rho equals 103 kg per cubic meter. If the orifice is at a depth h from the water surface in a tank, the gauge pressure there is P0 equals h rho g. Opening parenthesis. 1. By Torricelli's law of efflux, the velocity of efflux. Exercises Q17 page 55. The pressure of water inside a closed pipe is 3 times 105 nm2. This pressure reduces to 2 times 105 nm2 on opening the valve of the pipe. Calculate the speed of water flowing through the pipe. Density of water equals 1000 kg per cubic meter. Solution. Data. P1 equals 3 times 105 pascals, V1 equals 0, P2 equals 2 times 105 pascals, rho equals 103 kg per cubic meter. Assuming the potential head to be 0, i.e., the pipe to be horizontal, the Bernoulli equation is. Exercises Q18 page 55. Calculate the rise of water inside a clean glass capillary tube of radius 0.1 mm, when immersed in water of surface tension 7 times 10 to 2 N per meter. The angle of contact between water and glass is 0. The density of water equals 1000 kg per cubic meter, G equals 9.8 meters per square second. Solution. Given Black small square radius of capillary tube equals 0.1 millimeters. Black small square surface tension of water equals 7 times 10 to 2 N per meter. Black small square angle of contact equals 0 degrees. Black small square density of water equals 1000 kg per meter. Black small square acceleration due to gravity equals 9.8 meter per second. To find black small square height of water column inside the capillary tube. Formula. When a capillary tube of radius r is dipped in a liquid of density ρ and surface tension T, the liquid rises or falls through a distance. Exercises Q19, page 55. An air bubble of radius 0.2 mm is situated just below the water surface. Calculate the gauge pressure. Surface tension of water equals 7.2 times 10⁻² N per meter. Solution. Exercises Q20, page 55. 27 droplets of water, each of radius 0.1 mm, coalesce into a single drop. Find the change in surface energy. Surface tension of water is 0.072 N per meter. Solution. R equals 0.1 mm equals 0.1 times 10 to 3 m, T equals 0.072 N per meter. Let R be the radius of the single drop formed due to the coalescence of 27 droplets of mercury. Volume of 27 droplets equals volume of the single drop as the volume of the liquid remains constant. Exercises Q21, page 55. A drop of mercury of radius 0.2 cm is broken into 8 droplets of the same size. Find the work done if the surface tension of mercury is 435.5 dyne per centimeter. Solution. Let R be the radius of the drop and R be the radius of each droplet. Data. R equals 0.2 centimeters, N equals 8, T equals 435.5 dyne per centimeter. As the volume of the liquid remains constant, volume of N droplets equals volume of the drop. Exercises Q22, page 55. How much work is required to form a bubble of 2 cm radius from the soap solution having surface tension 0.07 N per meter? Solution. R equals 2 cm equals 2 times 10 to 2 m, T equals 0.07 N per meter. Initial surface area of soap bubble equals 0. Final surface area of soap bubble equals 2 times 4 pi r2. Therefore increase in surface area equals 2 times 4 pi r2. The work done equals surface tension times increase in surface area equals T times 2 times 4 pi r2. The work done equals 0.07 times 8 times 3.142 times 2 times 10 to 2 equals 7.038 times 10 to 4 J. Exercises Q23, page 55. A rectangular wire frame of size 2 cm times 2 cm is dipped in a soap solution and taken out. A soap film is formed if the size of the film is a change to 3 cm times 3 cm. Calculate the work done in the process. Surface tension of the soap film is 3 times 10 to 2 N per meter. Solution. Data. A1 equals 2 times 2 cm, 2 equals 4 times 10⁻4 meters 2. A2 equals 3 times 3 cm, 2 equals 9 times 10 to 4 m2, T equals 3 times 10 to 2 N per meter. As the film has two surfaces, the work done is W equals 2T, A2 A1 equals 2, 3 times 10 to 2, 9 times the 4th of April 10 times 10 to 4 equals 3.0 times 10 to 5 J equals 30 mu J.